So we're doing problem 14, which has two wires, both infinitely long, one with 10 amps traveling to the right, one with 10 amps traveling to the left, and we're instructed to find the magnetic field at points A, B, and C right here. So for this problem, we know that B is equal to mu naught I over 2 pi D, where I is the current and D is the distance from the wire. So that's the setup. I guess we can start with A, where we're going to have the B field from this wire, and we know that the current is going that way, so our fingers curl up, and we know that from the wire traveling to the right, we're going to have current coming out at us, or magnetic field, sorry, and then from the one traveling to the left, we're going to have a magnetic field going into the page, so we're good. And since we know that this one's closer, the magnetic field is going to be greater from that one, so we know that the net magnetic field at that point is going to be then, or out of the page. So we can write that by saying that the current, or the, magnetic field at A is going to be a combination of the magnetic field at wire 1 and the magnetic field at wire 2, which is going to be mu naught 10 for I over 2 pi, oh right, and the distance is 2 centimeters from here to here, and 4 centimeters here to here, 2 centimeters from there to there. I don't know how well you can see that. Pretty awesome. So then the distance here is going to be the 2 centimeters there, which is 0.02 meters. And then we're going to subtract from that B2 since they're opposite. So we're going to have mu naught 10 amps over 2 pi, and now we're going to have the 4 centimeters plus the 2 centimeters, so 0.06 centimeters, or meters, excuse me. So that is going to be our equation for the magnetic field at A, and if you evaluate that, you get that the magnetic field at A is equal to 6.7 times 10 to the negative 5th Teslas. And that's going to be coming out of the page. Hopefully 10 to the negative 5th T out. So that is what we're going to be getting for the magnetic field at A. Now if we look back up here, we can see some symmetry between A and C. So again, if we do our right hand rule, we'll know that the wire closest to C is going to be coming out at you because of how your fingers curl around, and then the wire farther away is going to be going in. So again, we're going to have a net force, or a net magnetic field, excuse me, out of the board at C, and it's going to actually have the same magnitude as at A because it's the same distance between the wires. So this answer here is actually the same as the magnetic field at C, so 6.7 times 10 to the negative 5th Teslas out. So that's both A and C. So now at point B, back up here, it's going into from the top wire and also into from the bottom wire, and we know that the distance here is 2 centimeters. Okay, so if we come back up to before where we wrote out the actual answer, where we're adding up B1 and B2, it's going to be the same magnitude, or they're going to be in the same direction, so we're adding them, but now they're actually going to be the same magnitude as well. So we're going to have mu naught times 10 amps over 2 pi times plus 0.02 plus mu naught 10 over 2 pi times 0.02. And so we're going to actually have the same magnitude of magnetic field from both of the wires. And then if you do that calculation, the B at point B ends up being 2.0 times 10 to the negative 4th Teslas, and that's, again, into the page. So those are your 2 answers, and that is how you go about solving them right there. That's about it.